Tonight, we will talk about neutron stars, what they are, how they form, and what truly happens after a star explodes. Whether you're drifting off to sleep or just relaxing with curiosity, you're in the right place. Let's begin at the end. The end of a star's life. Massive stars don't go gently. After burning their fuel over millions of years, a dramatic event takes place. A supernova explosion. This explosion is one of the most energetic events in the universe. For a brief moment, the star outshines entire galaxies. But what happens after the flash fades? That's when one of the strangest objects in the universe is born, the neutron star. Imagine a star many times more massive than our Sun. Throughout its life, it burns hydrogen, fusing atoms into helium, and then heavier elements like carbon and oxygen. As this process continues, the star forms an onion-like structure with increasingly heavy elements in its core. Eventually, it begins fusing iron. But fusing iron doesn't release energy. Instead, it consumes it. This marks the point of no return. The balance between gravity pulling inward and radiation pushing outward collapses. The star's core can no longer support itself, and it begins to implode under its own immense weight. In less than a second, the core collapses. The outer layers rebound off the suddenly rigid core and explode outward into space. This is the supernova. What's left behind, if the star was massive but not too massive, is a neutron star. So what exactly is a neutron star? Think of something with the mass of 1.5 suns squeezed into a sphere only about 20 kilometers wide, roughly the size of a city. That's a neutron star. It's so dense that a single teaspoon of neutron star material would weigh about 1 billion tons. It's not made of atoms in the traditional sense. The pressure is so extreme that electrons and protons have been crushed together into neutrons, hence the name. In this state, matter is no longer made of separate particles with space between them. It's an almost perfectly uniform sea of neutrons, packed tightly together by gravity that's billions of times stronger than Earth's. At the surface of a neutron star, gravity is so intense that if you dropped something from just 1 meter above, it would hit the surface in a fraction of a microsecond, at over 7 million kilometers per hour. There's no atmosphere in the way we experience it. What exists is a thin layer of supercompressed material, and beneath it, a crust of degenerate matter unlike anything on Earth. Time behaves strangely near a neutron star. According to general relativity, gravity affects time. Stronger gravity slows it down. Near the surface of a neutron star, time moves significantly slower than it does far away in space. If you could somehow stand on a neutron star, which is impossible without being instantly crushed, time for you would pass measurably slower than for someone floating nearby. The magnetic fields of neutron stars are also extreme. Some of them, known as magnetars, have magnetic fields a quadrillion times stronger than Earth's. These fields are so powerful they can distort atoms, pulling electrons into thin spindles and even interfere with electronics at great distances. But how do we even detect neutron stars? After all, they're incredibly small and don't emit much visible light. Many neutron stars are observed as pulsars. These are neutron stars that emit beams of radiation from their magnetic poles. As the star spins, sometimes hundreds of times per second, these beams sweep across space like lighthouse beams. If Earth happens to lie in the path of one of these beams, we detect a regular pulse of energy. That's a pulsar. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell. At first, the pulses were so regular, like a ticking clock, that astronomers wondered if it could be a signal from intelligent life. They jokingly labelled it LGM1, short for Little Green Men, but soon more were found, and it became clear that these were natural phenomena, rapidly spinning neutron stars. The pulses are not light in the visible spectrum, but in radio waves, X-rays, or gamma rays, depending on the pulsar. Some spin incredibly fast, hundreds of times per second. These are called millisecond pulsars and are among the most accurate timekeepers in the universe, rivaling atomic clocks. But even without their pulses, neutron stars reveal themselves through their effects on nearby stars. In binary systems, where a neutron star orbits with a normal star, the immense gravity of the neutron star can pull material off its companion. As this material spirals in, it heats up and emits X-rays. These are known as X-ray binaries. Neutron stars are not eternal. Over time, they cool and slow down. The radiation beams weaken, but their incredibly dense matter remains. Some scientists believe that inside a neutron star, deeper than we can ever observe, matter may reach even stranger states, like quark matter, where neutrons themselves break apart into their constituent quarks. This region, if it exists, would be even denser and more exotic than anything we can study in laboratories. Interestingly, neutron stars also give us a window into the fundamental laws of physics. They let us study gravity, nuclear forces, and even quantum effects at scales far beyond what we can achieve on Earth. For example, in 2017, scientists observed gravitational waves from the collision of two neutron stars. This event, called GW 79817, was a breakthrough. Gravitational waves are ripples in space-time caused by massive objects accelerating. When two neutron stars spiral into each other and merge, they send out a burst of gravitational waves across the cosmos. Instruments like LIGO and Virgo on Earth can now detect these tiny disturbances. The GW 79817 event also emitted visible light, gamma rays, X-rays, and radio waves. A cosmic symphony that gave us insight into how elements like gold and platinum are forged in space. That's right, heavy elements like gold are not made in regular stars. They're made in extreme events like neutron star collisions. When these stars smash together, the energy released is enough to fuse atoms into the heaviest elements in the periodic table. So, in a very real sense, the jewelry we wear, or the circuitry in our devices, owes its origin to the death and collision of stars. So what happens after a star explodes? It can become a neutron star, a spinning, ultra-dense magnetic object, sometimes flashing pulses across the universe. It's a graveyard for ordinary matter, and yet a birthplace for heavy elements. It's the quiet heart left behind after the storm of a supernova. Neutron stars sit at the edge of physics. They're not quite black holes, which we'll talk more about later, but they're no longer normal matter either. There's something in between, and though they seem small and dim, they may hold the keys to understanding the forces that govern everything, from the tiniest particles to the largest galaxies. As you listen tonight, let this thought linger. Even in death, stars create. Even in collapse, they hold secrets of creation. Neutron stars are among the universe's most profound paradoxes, born from destruction, yet brimming with mystery and possibility. Rest easy knowing the cosmos is full of wonders, strange, dense, beautiful ones, watching silently from the depths of space. To truly understand neutron stars, we have to travel deeper into the heart of matter itself. Most of what we consider solid, rocks, metals, even your own body, is made of atoms. But atoms are mostly empty space. If an atom were the size of a stadium, the nucleus at its center would be the size of a pea, with electrons whirling in the vast space around it. But in a neutron star, that space has been erased. The atoms have collapsed under such intense gravity that matter has been crushed into something profoundly unfamiliar. Let's rewind again to the moment just before the supernova. As a massive star reaches the end of its life, the battle between pressure and gravity is lost. Gravity wins, the core collapses. Protons and electrons are forced so close together by the overwhelming pressure that they fuse into neutrons. This process is called neutronization. It happens in milliseconds and releases a burst of neutrinos, tiny, nearly massless particles that escape into the universe by the trillions. What's left behind is essentially a giant atomic nucleus the size of a city. But it doesn't behave like an atomic nucleus at all. The outer crust of a neutron star is a solid lattice of nuclei immersed in a sea of free electrons. Below this crust lies the inner crust, where nuclei become increasingly neutron-rich and start to dissolve. Deeper still, the nuclei break apart completely, and what remains is a sea of unbound neutrons, with a few protons and electrons mixed in. This incredibly dense region is called neutron degenerate matter, and it follows physics we barely understand. Normal pressure cannot support such matter. It's held up by degeneracy pressure, a quantum mechanical force that arises because two neutrons cannot occupy the same quantum state. This is a consequence of the Pauli exclusion principle, a cornerstone of quantum theory. In a neutron star, this quantum pressure pushes back against the star's immense gravity, halting the collapse, at least temporarily. If the star were just a little more massive, even this pressure would not be enough, and the object would collapse further into a black hole. In this way, neutron stars exist on a razor's edge between stability and total collapse. They are nature's tightrope walkers, balanced between the known and the unknown. Now consider the density of these stars again. One sugar cube-sized piece of neutron star would weigh as much as Mount Everest. If you could hold it, which you couldn't, it would fall through the earth like a bullet through paper, but you wouldn't be able to get near it in the first place. Its gravity would tear your atoms apart long before you arrived. And yet, neutron stars are not lifeless. Many of them spin at incredible rates. They are born spinning, thanks to the conservation of angular momentum. Think of a spinning ice skater. As the skater pulls in their arms, they spin faster. When a massive star collapses into a tiny neutron star, it spins faster for the same reason. A star that once rotated once every few days might collapse into a neutron star rotating dozens or even hundreds of times per second. Some neutron stars spin so fast they become millisecond pulsars. These are among the most stable rotators in the universe. They slow down incredibly gradually over millions of years. Scientists have used these cosmic metronomes to test the nature of time itself. In fact, timing the arrival of their pulses allows astronomers to detect subtle effects, like the warping of space-time by gravity or the gravitational pull of invisible companions. The magnetic fields of neutron stars also become vastly amplified during collapse. What was once a strong magnetic field in a regular star becomes unimaginably powerful in the much smaller neutron star. The magnetic field lines are pulled tight and concentrated, much like the spin. This process can create magnetic fields 1,000,000 billion times stronger than Earth's. And with these fields come incredible energies. When the magnetic axis is not aligned with the rotational axis, the neutron star emits beams of radiation from its poles. These beams sweep across space, If they cross our line of sight, we observe pulses, hence a pulsar. These beams are powered not by heat, but by rotational energy. Over time, the star's spin slows down as this energy is gradually radiated away. Some pulsars are so regular, so precise, that they rival atomic clocks. In fact, arrays of pulsars are now being used to detect gravitational waves from the distant universe. By observing tiny shifts in the arrival times of their pulses, astronomers can detect ripples in the fabric of space-time caused by titanic events billions of light years away. Then there are magnetars. These are neutron stars with the strongest magnetic fields ever observed in the universe. A magnetar's field is so intense that it can twist and crack the solid crust of the star, releasing bursts of X-rays and gamma rays. Some of these bursts are powerful enough to affect satellites and electronics on Earth, even from thousands of light years away. In 2004, a burst from a magnetar called SGR 1806-20 released as much energy in a tenth of a second as the Sun emits in 100,000 years. And yet, the star itself remained intact. It had merely shifted, trembled slightly, and in doing so reminded us of the raw power contained in these cosmic remnants. It's worth remembering that neutron stars are incredibly small on astronomical scales. The Sun is 1.4 million kilometers across. A neutron star is only about 20 kilometers wide. And yet, despite being smaller than many cities, they pack in more mass than our Sun. That kind of density is beyond everyday comprehension. If Earth were compressed to the density of a neutron star, it would be just a few hundred meters wide. Because of their small size and dim nature, neutron stars are hard to detect. Most are discovered via their pulses, or through X-ray emissions from binary systems. Some are detected when they pass in front of background stars, bending their light due to gravitational lensing. But many likely remain invisible, cold, dark, and quiet, drifting alone through space. Yet despite their silence, neutron stars are crucial to our understanding of the cosmos. They provide laboratories for testing extreme physics. They offer clues about the behavior of matter at densities that we can't reproduce on Earth. They let us study gravity, magnetism, and the life cycles of stars. And when they collide, they light up the universe with gravitational waves and create the elements that form planets, people, and all the richness of matter we see around us. Neutron stars are, in many ways, time capsules. They are the remnants of stars that lived and died long before Earth existed. Some of the neutron stars we observe today exploded as supernovae millions or even billions of years ago. Their light has taken eons to reach us. And yet, through their pulses, they continue to speak, ticking out their rhythms across time and space. So as we look up into the night sky, remember this. Behind the veil of stars, beyond the glimmer of light, lie the silent echoes of stellar death. Not as empty ruins, but as compact, powerful reminders that even in collapse, the universe creates something new. Neutron stars are more than leftovers. They are messengers. They are engines. They are mysteries still unfolding. And in their quiet spin, they remind us how much more there is to discover. To understand just how alien neutron stars are, we have to step even further away from our usual experience of matter, space, and time. These stellar remnants don't just challenge our knowledge of astrophysics, they redefine it. Let's start with the surface of a neutron star. Unlike any planet or star we know, a neutron star's surface is essentially a shell of atomic nuclei crushed into an ultra-dense crust. Temperatures can reach over 1,000,000 degrees Kelvin even long after formation. Yet because of their small size, neutron stars emit only faint light compared to their earlier lives as massive glowing stars. The surface isn't smooth, it's rigid. Imagine a crust of iron, compressed far beyond anything possible on Earth, stretched over a core of neutrons. This outer shell is believed to be extraordinarily hard. Some scientists suggest it may be the strongest material in the universe. A mountain on a neutron star could be less than a millimeter tall, but would weigh billions of tons. These tiny deformations in the crust may be responsible for some of the bursts of radiation we detect. Beneath this crust lies the superfluid interior. Yes, superfluid, matter that flows without friction. At the densities inside a neutron star, neutrons form a quantum fluid that behaves in extraordinary ways. In this state, neutrons can form vortices, whirlpools that store the star's rotational energy. These quantum vortices are key to understanding some of the most fascinating behaviors of pulsars. For example, many pulsars gradually slow down over time, but occasionally they experience a sudden increase in spin rate, something known as a glitch. These glitches are thought to be caused by interactions between the superfluid core and the solid crust. When angular momentum is suddenly transferred from one to the other, the entire star spins up, briefly and measurably. We can detect these tiny shifts from Earth, even though they occur thousands of light years away. It's a reminder that neutron stars are not static. They are dynamic, evolving objects, constantly shifting between equilibrium and disturbance. Now, consider how these stars came to exist. A massive star lives for millions of years, fusing lighter elements into heavier ones. But the process of fusion, while long-lived, is ultimately doomed. Once iron forms in the core, no further energy can be extracted from fusion. Gravity takes over. The collapse of the core is so rapid, so violent, that it generates a shockwave strong enough to blow off the outer layers of the star. This moment, this supernova, is a kind of rebirth. And yet it leaves behind a star that's no longer burning, no longer fusing, but still incredibly hot and dense. The pressure within it is so immense that light struggles to escape. In fact, some neutron stars are so dense that they come just short of becoming black holes. They exist right at the boundary of gravitational collapse. How close are they? There's a theoretical limit called the Tolman-Oppenheimer-Volkoff limit, which is the maximum mass a neutron star can have before collapsing into a black hole. This limit is estimated to be around 2.1 to 2.3 solar masses. Above this threshold, not even neutron degeneracy pressure, the force that holds the star up, can withstand gravity. What happens beyond that point? Collapse continues, unstoppable, until a singularity forms, a black hole. But if the mass remains under that threshold, the neutron star remains stable, balanced by quantum forces that defy everyday logic. Some neutron stars rotate with breathtaking speed. The fastest known pulsar spins over 700 times per second. That means the surface of the star is moving at about 20% the speed of light. This is not theoretical, it's measured. The precision of pulsars makes them excellent tools for studying motion, acceleration, and gravitational interactions on cosmic scales. In fact, some pulsars exist in binary systems with other neutron stars, or even white dwarfs or regular stars. These binaries are cosmic laboratories. By observing the timing of their pulses and the gravitational effects on their companions, astronomers can test predictions from Einstein's theory of general relativity with astonishing accuracy. One such system, PSR J0737 to 3039, is a double pulsar, two neutron stars orbiting one another, both emitting regular pulses. As they orbit, their gravitational fields interact, creating tiny deviations in timing that match exactly what general relativity predicts. These systems provide some of the most stringent tests of gravitational physics outside of black holes. The idea that collapsed stars can still serve as tools for measuring the universe is remarkable. These are objects formed in the chaos of stellar death, and yet they offer order, precision, and insight. Now let's step beyond observation and into theory. What lies at the very core of a neutron star? It's one of the biggest mysteries in modern astrophysics. Some researchers believe that the center may contain quark matter, a state of matter where neutrons themselves dissolve into their constituent parts, up and down quarks. If true, this would mean that inside some neutron stars lies an even stranger phase of matter, a quark-gluon plasma, similar to what existed in the first microseconds after the Big Bang. We cannot reproduce these conditions on Earth. Even the Large Hadron Collider, the most powerful particle accelerator on the planet, falls short of reaching the densities and pressures found inside a neutron star. So we rely on models, simulations, and observations, watching for tiny clues that might hint at what lies inside. If quark matter does exist inside neutron stars, then perhaps some of them aren't truly neutron stars at all, but something even more exotic: quark stars. These hypothetical objects would be even smaller and denser than neutron stars. So far, no such object has been definitively identified, but some peculiar observations have fueled speculation. Neutron stars also allow us to explore the limits of the periodic table. The heavy elements forged during neutron star collisions, like gold, platinum, and uranium, are created in seconds during cataclysmic mergers. This process, called R-process nucleosynthesis, requires extreme conditions: high neutron density, high energy, and rapid cooling. When neutron stars merge, vast quantities of neutron-rich material are ejected into space. These neutrons are captured by atomic nuclei, creating new, heavier elements in rapid succession. Over the following days, the glowing debris, called a kilonova, radiates across the spectrum. It's a brief but powerful show of creation emerging from destruction. Thanks to the simultaneous detection of gravitational waves and light from these events, astronomers can now pinpoint where and when heavy elements are born in the universe. It's no longer theory, it's observation, and so the quiet neutron star, once the silent remnant of a supernova, becomes a cosmic alchemist, fusing matter into the materials that will one day become planets, minerals, and maybe even life. We often imagine space as empty, quiet, and still. But neutron stars remind us that the universe is alive with motion and transformation. These tiny, ultra-dense objects spin, pulse, collide, and evolve. They whisper across galaxies with their radiation, they warp space-time with their mass, and sometimes they shake the very fabric of the universe with their gravitational waves. Neutron stars are not simply leftovers from dead stars. They are dynamic, complex, and constantly influencing the universe around them. Though they no longer shine like their former selves, they remain essential players in the grand cosmic drama. From the moment of collapse to the slow cooling over billions of years, every phase of a neutron star's life tells a story of extremes. Extreme density, extreme gravity, extreme physics. They are the densest visible matter in the cosmos, and among the most precise tools in astrophysics. And through their quiet persistence, they teach us not everything that dies is gone. Not everything that ends is over. In the universe, even the wreckage of stars can become the instruments of deeper understanding. Now that we've explored the formation and nature of neutron stars, let's turn our attention to one of the most astonishing phenomena they create: collisions. When two neutron stars spiral into each other and merge, the universe doesn't just tremble, it transforms. First, let's understand how two neutron stars end up in a deadly dance to begin with. Many stars in the universe are born as binaries, pairs that orbit a common center of gravity. If both stars are massive enough, each may eventually go supernova, leaving behind two neutron stars. Over time, these two stellar remnants orbit each other in an extremely tight spiral. As they revolve, they emit gravitational waves, ripples in space-time, slowly draining energy from the system. The result? The stars spiral closer and closer together over millions or even billions of years, until, at last, they collide. This moment is one of the most dramatic in the cosmos. When the two neutron stars crash together, their surfaces collide at a significant fraction of the speed of light. The resulting explosion is called a kilonova, and it releases not just light and radiation, but also gravitational waves and, crucially, heavy elements. The universe, in this moment, forges gold, platinum, and rare earth metals in enormous quantities. In 2017, astronomers made history when they detected such a collision. Two neutron stars located 130 million light-years from Earth merged in a galaxy called NGC 4993. The gravitational waves from the event, known as GW17-EO817, were picked up by the LIGO and Virgo observatories. Just 1.7 seconds later, a burst of gamma rays was detected by space telescopes. And within hours, astronomers around the world pointed their instruments at the patch of sky where the signal originated. For the first time, we witnessed a neutron star merger not just through gravitational waves, but also in visible light, infrared, X-rays, and radio. It was the dawn of a new era in astronomy, multi-messenger astronomy, where we observe the same event through different channels of information. The light from the merger faded quickly, but what we saw in that brief window answered long-standing questions. Spectral analysis revealed the signatures of heavy elements being formed, proof that such cosmic collisions are indeed responsible for much of the gold and platinum in the universe. These elements were created in seconds, forged in the intense neutron-rich environment that only a neutron star collision can provide. This single event rewrote textbooks and confirmed decades of theoretical predictions. It showed us that even in their final moments, neutron stars shape the universe in profound ways. But what happens to the neutron stars after they merge? That depends on their combined mass. If the mass is below a certain threshold, they may form a hypermassive neutron star, a temporary, rapidly spinning object held up by its own rotation and internal pressure. But this state is unstable. Within seconds or minutes, it collapses into a black hole. In other cases, the merger may produce a black hole immediately. The key factor is whether neutron degeneracy pressure, the quantum force that resists further collapse, can still hold. If not, the object becomes dense enough to form a singularity, hidden behind an event horizon. Before that happens, though, the surrounding debris can form an accretion disk, a swirling, superheated cloud of matter spiraling into the black hole. This disk emits intense radiation and can launch powerful jets of material at nearly the speed of light. These jets are thought to produce short-duration gamma-ray bursts, among the most energetic explosions in the cosmos. All of this, gravitational waves, heavy elements, light across the spectrum, comes from a collision that lasts only a fraction of a second. But even single neutron stars can create cosmic drama. Sometimes, isolated neutron stars undergo what's known as a starquake. The rigid crust, under extreme stress from the star's magnetic field or changes in rotation, can suddenly crack. This violent rearrangement can release enormous energy in the form of X-rays or gamma rays, especially in magnetars, whose intense magnetic fields store colossal amounts of potential energy. These starquakes are not theoretical. We've seen their effects. In 1998, a sudden flare from the magnetar SGR 1900+14 bathed Earth in high-energy photons. For a brief moment, it was the brightest source of gamma rays in the sky. If it had been much closer, the event could have disrupted satellites or even our upper atmosphere. This reminds us of the immense energy locked within these stars. Energy that, when released, can briefly rival the output of an entire galaxy. But neutron stars don't only give off energy, they also absorb it. Some neutron stars capture matter from companion stars, drawing in gas through accretion. As this material spirals in, it compresses, heats up, and emits X-rays. These systems are called X-ray binaries, and they are among the brightest X-ray sources in the sky. As more matter falls in, the neutron star gains mass. If it reaches the Tolman-Oppenheimer-Volkoff limit, it will collapse into a black hole. In this way, neutron stars can evolve even after their formation, not through fusion, but through the physics of mass, pressure, and gravity. This process of accumulation and collapse is just another phase in the life cycle of matter. But perhaps the most compelling role of neutron stars lies in what they teach us about fundamental physics. They allow us to test general relativity under extreme conditions. They challenge our models of nuclear matter. They act as cosmic clocks, laboratories, and even factories of heavy elements. No other known object in the universe does all this while being no larger than a city. Think of what that means. In the same volume that holds a small human town, nature has packed the mass of several suns, the power to bend light, the ability to warp time, and the potential to craft the elements we hold most precious. When we look at neutron stars, we're seeing nature at its most compact, efficient, and unforgiving. They are stripped down physics, matter boiled down to its core ingredients, held together by gravity and quantum mechanics. And while they may seem distant, abstract, or invisible, their story is part of ours. The atoms in your blood, your bones, and your brain were born in stars. Some were forged in the gentle fires of long-lived suns. Others were made in the momentary fireballs of neutron star collisions. You are, in part, the product of a universe where stars explode, collapse, spin, and merge. Neutron stars are part of that heritage. Their pulses echo across time. Their collisions color galaxies. Their magnetic tantrums shake space itself. And their secrets remain, waiting, quiet, enduring, as the rest of the cosmos continues to unfold around them. Let's now zoom out and consider the role of neutron stars in the grand structure of the universe. These objects may be tiny on cosmic scales, but their influence is far-reaching. They don't just form in isolation, they shape galaxies, trace the history of stellar populations, and serve as cosmic timekeepers that map the very structure of space-time. Start with the idea of a pulsar timing array. Astronomers have realized that by carefully measuring the arrival times of pulses from many millisecond pulsars across the sky, They can use these neutron stars as a vast galactic observatory. This is not just a poetic metaphor, it's real. Because pulsars are such reliable timekeepers, tiny deviations in the timing of their signals can reveal the presence of gravitational waves from supermassive black holes orbiting each other in distant galaxies. In June 2023, astronomers announced the detection of low-frequency gravitational waves, ripples in space-time that had traveled across billions of light-years. These waves weren't created by neutron stars themselves, but the pulsars acted as detectors, recording the subtle tremble in space-time as the waves pass through. Neutron stars, then, are not only sending information, they are receiving it. Their existence allows us to feel the distant, invisible dance of massive objects far beyond our own galaxy. And this brings us to the idea that neutron stars are not just remnants, they are records. The characteristics of a neutron star, its mass, spin, magnetic field, and temperature, are imprints of the life it once lived. A fast-spinning pulsar might have once been part of a binary system, spun up by the transfer of angular momentum from a companion. A slowly rotating, isolated neutron star may have formed alone. A magnetar's extreme field might hint at rapid rotation during its collapse. In other words, neutron stars are fossils of stellar evolution. By studying them, we reconstruct the lives of stars that burned bright and died long before humanity even existed. In this way, each neutron star is a historical document, a frozen endpoint in the life cycle of matter. But their story doesn't stop there. As neutron stars cool over time, their thermal radiation fades. Newly formed neutron stars can glow in X-rays for hundreds of thousands of years. But eventually, they become cold and nearly undetectable. Some may become invisible to our instruments, drifting as dark, dense remnants through the galaxy. These invisible neutron stars could number in the hundreds of millions in our galaxy alone. The Milky Way is a galaxy of about 200 billion stars, and estimates suggest that for every massive star that died in a supernova, a neutron star may have been left behind. Most of these are too faint or too old for us to see. Occasionally, one might betray its presence. For example, if a neutron star passes through a cloud of interstellar gas, it may accrete material, heat up slightly, and emit faint X-rays. Or, in rare cases, gravitational lensing may reveal its existence when it passes in front of a background star, bending and magnifying the light behind it. Even in darkness, they influence their surroundings. Neutron stars also serve as anchor points for galactic maps. Because pulsars are distributed throughout the Milky Way, and because their signals travel at the speed of light, astronomers can use them to probe the interstellar medium, the gas and dust between stars. As pulsar signals travel through this medium, they are dispersed and delayed in frequency-specific ways. By analyzing these delays, scientists can infer the density and composition of the material they pass through. In this way, neutron stars help us explore the structure of the galaxy itself, and they're not just confined to the Milky Way. We've detected neutron stars in other galaxies as well. When the 2017 neutron star merger occurred, its light was traced to a galaxy 130 million light-years away. This proved that these events are not unique to our corner of the universe. They're cosmic, common, and vital to the evolution of matter everywhere. Some neutron stars live in globular clusters, ancient spherical collections of stars that orbit galaxies like halos. These environments are ideal for forming millisecond pulsars through stellar interactions. In fact, some clusters contain dozens of pulsars packed into tiny volumes of space. These serve as dense gravitational laboratories, places where stars collide, exchange partners, and evolve in complex dances. And then there are the so-called zombie stars, neutron stars that pull matter from companions and reignite, glowing brightly in X-rays. These accreting neutron stars blur the line between death and rebirth. Though their cores have collapsed, they remain active through their interactions, feeding on their surroundings and changing form. This raises a question that seems almost philosophical. When is a star truly dead? If a collapsed core still rotates, emits beams, releases radiation, and influences its environment, has it truly ended? Or is it living in another form, stripped of fire but rich in force? Neutron stars challenge the idea that endings are final. In the universe, transformation is the rule, not extinction. They also challenge our understanding of space and time. Near the surface of a neutron star, space-time is curved so strongly that clocks tick more slowly compared to distant observers. This gravitational time dilation is measurable. In fact, precise timing of pulsars has confirmed predictions from Einstein's theory of general relativity again and again. The gravitational redshift, the stretching of light to longer wavelengths as it escapes the intense gravity of the star, is another signature of the warped space-time surrounding these dense objects. We don't just infer gravity from motion, we see it bending time and light directly. And yet, for all their extremity, neutron stars obey the same fundamental laws that govern you and me. Gravity, electromagnetism, nuclear forces, and quantum mechanics all converge in these stars. The difference is one of scale and intensity. By studying neutron stars, we don't leave our physics behind. We extend it into new regimes. It's like pushing a car engine until it breaks, not to ruin it, but to understand its limits. Neutron stars are nature's way of showing us where physics bends, stretches, and sometimes surprises us. And perhaps the greatest surprise is how consistent, elegant, and interconnected it all is. A star burns hydrogen in its core. Over time, it fuses heavier and heavier elements. Then it explodes, collapsing into a neutron star. That neutron star might spin and pulse for millions of years. It might collide with a sibling and forge gold. It might disappear into darkness. Or it might, one day, fall into a black hole and vanish behind the veil of an event horizon. Every step is part of a chain. No stage is wasted. No process is random. The story of a neutron star is the story of the cosmos at its most efficient and expressive. From the first atoms to the final collapse, neutron stars are not detours in the journey of matter. They are milestones. Let's now turn our attention inward, deep into the structure of a neutron star itself. If you could somehow survive the gravitational crush and take a journey toward the center of one of these dense remnants, what would you find? The answer is not simple. In fact, it might be one of the most tantalizing unknowns in modern physics. The outermost layer of a neutron star is called the crust. It's unlike anything on Earth. The very surface is believed to consist of tightly packed atomic nuclei, mostly iron, arranged in a solid lattice. Imagine a planetary crust, but billions of times denser, and with pressures so high that the electron clouds surrounding each atom are crushed together. This surface is only a few hundred meters thick, but beneath it lies something even stranger. As you descend, you pass through layers where atoms lose their structure entirely. Electrons are forced into the nuclei, combining with protons to form neutrons. What you get is a sea of neutrons and a soup of other subatomic particles, packed together in exotic ways. This forms the inner crust, where the pressure has become so intense that atomic structure ceases to exist in any recognizable form. The nuclei are squeezed into bizarre shapes, spaghetti-like strands, lasagna-like sheets, or even bubble-like voids. Physicists refer to this as nuclear pasta, not for humor, but because these shapes represent real predictions of how nuclear matter behaves under immense stress. But this is only the beginning. Dive deeper still, and you enter the outer core. Here, neutrons dominate. They move in a superfluid state, flowing without friction, intermixed with a small population of protons and electrons. The conditions here are ideal for superconductivity and superfluidity, where electrical resistance drops to zero and quantum mechanical effects stretch across kilometers of dense stellar matter. It's difficult to overstate the alienness of this environment. You are no longer inside anything resembling matter as we know it. You're in a quantum ocean of degenerate particles, where the rules of conventional chemistry and biology have broken down entirely. And still, we go deeper. At the very center, the inner core, theories begin to diverge. No one knows for sure what lies in this region, because our current physics can't fully describe matter under such extremes. Some theories suggest it may contain exotic particles, hyperons, which include strange quarks, or even a state of matter known as quark-gluon plasma. This would be matter in its most fundamental form, not made of protons or neutrons, but of the quarks and gluons that make up those particles themselves. If this is true, then the core of a neutron star is not just dense, it's a relic of the earliest moments of the universe, when quarks roamed freely in the hot, dense fireball of the Big Bang. If we could study this matter directly, we might learn how the strong nuclear force behaves under unimaginable pressure, knowledge that could lead to new physics, even new technologies someday. Unfortunately, we can't see inside a neutron star. We infer its interior from measurements, its mass, its radius, its spin, and the way it emits radiation. The relationship between a neutron star's mass and its radius, the so-called equation of state, gives us clues about what's going on inside. If we find a neutron star that's more massive than our models predict it can be, that tells us something about the stiffness of the matter in its core. Conversely, if a neutron star is smaller than expected for a given mass, that suggests a softer, more compressible interior, maybe even something exotic. This is where telescopes like NICER, the Neutron Star Interior Composition Explorer, come in. NICER, mounted on the International Space Station, observes X-rays from neutron stars with unprecedented precision. By watching how X-rays fluctuate as a star rotates, NICER can measure hotspots on the surface and determine how the star's gravity bends light. This allows astronomers to make detailed inferences about the star's shape and structure. Already, NICER has revealed that some neutron stars are more massive and compact than we thought. This pushes our understanding of matter into new territory, and possibly toward a new chapter in physics. But we're not limited to space-based telescopes. Ground-based experiments like those at the Large Hadron Collider aim to recreate, for fleeting moments, the kind of extreme matter that might exist in a neutron star core. Smashing heavy ions together at near light speed, they probe the behavior of quarks and gluons under high temperature and density. It's ironic, in a way. We build billion-dollar machines here on Earth to mimic what a single neutron star does naturally, quietly, efficiently, and constantly, somewhere in the galaxy. The physics of neutron stars sits at the intersection of many disciplines: nuclear physics, particle physics, quantum mechanics, general relativity, and astrophysics. These are not just dead stars, they're cosmic laboratories. They give us a stage on which the universe's deepest rules are played out. One particularly fascinating consequence of these extreme conditions is the presence of superfluid vortices. In a neutron star's interior, where neutrons flow as a superfluid, rotation doesn't occur the way it does in ordinary fluids. Instead, the angular momentum is quantized. It exists in discrete chunks, forming an array of tiny tornado-like vortices that carry the rotation. As the star spins down over time, these vortices move and rearrange. Occasionally, they may get pinned to the crust. When they suddenly unpin, they transfer angular momentum back to the star's outer layers. This leads to a phenomenon called a glitch, a sudden jump in the rotation speed of a pulsar. Glitches have been observed in multiple pulsars, and they offer one of the few direct windows into the internal dynamics of these enigmatic objects. Think about that. A ripple in quantum fluid happening 10 kilometers beneath the surface of a collapsed star, 10,000 light-years away, causes a flicker in a radio signal we detect here on Earth. This is science at its most elegant. So, what are we really studying when we observe a neutron star? We're studying the behavior of nature under pressure. Extreme pressure. We're watching what happens when particles are forced into impossible configurations, when gravity crushes and compacts and curls space-time into steep wells. And in return, we get answers, not just about stars, but about reality itself. We get hints about the early universe, about matter's fundamental limits, about forces we have yet to fully understand. And perhaps most importantly, we get questions. Because for every neutron star we study, there are dozens we can't yet see. For every theory we test, there are corners of the star we can't yet probe. These dense spheres of collapsed light and matter are not just remnants, they are riddles. Each one is a silent question spinning through the dark. Now that we've explored the exotic inner structure of neutron stars, it's time to consider their behavior over time. These are not static objects. Neutron stars evolve. They spin, they cool, they collide, and in doing so, they shape the cosmos in subtle but profound ways. When a neutron star is born, it is unimaginably hot, reaching temperatures of up to 1 trillion degrees Kelvin. But it doesn't stay that way for long. Within minutes, the star begins to cool rapidly, emitting an enormous flood of neutrinos. These nearly massless particles escape the dense star with ease, carrying away most of the initial heat. Within a few years, the neutron star cools to about 1 million degrees. Still incredibly hot, but far colder than it started. From there, it continues to cool, but very slowly, losing heat over tens of millions of years. Eventually, it may become cold and nearly invisible, a dark neutron star detectable only through gravitational interaction. But temperature is only part of the story. One of the most noticeable characteristics of many neutron stars is their rotation. Newborn neutron stars can spin extremely fast, sometimes hundreds of times per second. These are known as millisecond pulsars, and they emit beams of electromagnetic radiation, like a lighthouse sweeping across the cosmos. If one of these beams crosses Earth, we see it as a pulse of light, hence the name pulsar. What's extraordinary is how stable these pulses can be. Some pulsars are more accurate than atomic clocks, maintaining their rhythm for millions of years. Astronomers use these cosmic metronomes to study everything from gravitational waves to the structure of our galaxy. Over time, however, neutron stars slow down. As they emit radiation, they lose energy. Their spin rate decreases, gradually stretching out the interval between pulses. Some stars slow so much that they eventually become radio silent, no longer detectable as pulsars. But not all is lost. In some cases, a neutron star can gain a second wind. This can happen in a binary system, when a neutron star is paired with another star. If the companion star evolves and begins to swell, it can transfer matter to the neutron star through a process known as accretion. As this material spirals in, it transfers angular momentum, spinning the neutron star up again. This rejuvenated object becomes a recycled pulsar, a previously aging neutron star that has been reborn with incredible speed. Some recycled pulsars rotate over 700 times per second. That's faster than the blades of a kitchen blender. These systems are not just energetic, they are also crucial laboratories for testing Einstein's general relativity. Because the timing of the pulses is so precise, astronomers can track the orbits of these binaries with astonishing accuracy. Any deviations from Newtonian predictions stand out, offering a direct test of how gravity behaves in strong fields. One famous example is the Hulse-Taylor binary pulsar, discovered in 1974. This system provided the first indirect evidence for the existence of gravitational waves. As the two neutron stars orbited one another, they lost energy in a way perfectly consistent with gravitational wave emission. This was long before LIGO or Virgo had detected any such waves directly. Yet the behavior of this one pulsar pair foretold what would later become one of the most groundbreaking discoveries in modern physics. Neutron stars don't just give, they also take. When two neutron stars are locked in a binary orbit, they can eventually spiral inward and collide. This dramatic event is called a neutron star merger, and it's one of the most powerful explosions in the universe. In 2017, astronomers observed such a collision for the first time, an event named GW 17817. Detected first as a ripple in space-time by LIGO and Virgo, it was followed by a brilliant flash of light across the electromagnetic spectrum. For the first time, humanity had seen both gravitational waves and light from the same cosmic event. The collision of these two neutron stars released more energy in seconds than the Sun emits in 1 billion years. It created a kilonova, a burst of light driven by the radioactive decay of heavy elements. And not just any elements, gold, platinum, and uranium. The collision forged them in vast quantities, ejecting them into space. This single merger produced more gold than all the gold mined on Earth throughout human history. This is where neutron stars become more than just astrophysical oddities. They are cosmic alchemists, factories of the universe's heaviest elements. Everything heavier than iron must be made in extreme environments, and neutron star mergers are one of the primary ways this happens. If you wear a gold ring or hold a platinum coin, you're in contact with matter created in the fiery death spiral of a neutron star pair. That's not just poetic, it's literal. What happens after a neutron star collision? The outcome depends on mass. If the two stars are relatively light, they may merge into a larger neutron star, briefly stable, then collapsing into a black hole. If they are heavier, they may collapse almost immediately into a black hole, leaving only a faint electromagnetic afterglow and a gravitational ripple behind. In some scenarios, the collision may produce a magnetar, an exceptionally magnetic type of neutron star. We'll explore those more in a moment. But in any case, the merger remnant is surrounded by debris, a swirling, glowing disk of matter spinning around the new central object. This disk emits intense radiation and drives powerful outflows. These outflows seed the surrounding galaxy with heavy elements, enriching the interstellar medium and paving the way for the next generation of stars and planets. These events are rare, estimated to happen perhaps once every 10,000 to 100,000 years in a galaxy like ours, but they are among the most important in cosmic evolution. Because they generate both gravitational and electromagnetic signals, they allow for a new kind of astronomy, multi-messenger astronomy. With it, we can study the universe not just through light, but through the subtle trembling of space-time itself. This marks a new era in science, one in which neutron stars are not merely remnants of stellar death, but key actors in the unfolding story of the cosmos. And what does this mean for us? It means we live in a universe where the death of one star can ripple across space and time, spark the creation of precious elements, and illuminate the deep rules of nature. It means the night sky is not just silent, it's filled with distant pulses and echoes, the residue of cataclysm and creation. And it means that somewhere, far from Earth, two neutron stars may already be on a collision course, moving silently toward one another, destined to meet in a flash of gold and gravity. A cosmic clock is ticking, and when it strikes, the whole universe will feel it. By now, we understand that neutron stars are dense, dynamic, and sometimes explosive, but among their many forms, one stands out as truly extreme: the magnetar. Magnetars are a special class of neutron stars with magnetic fields 1,000 times stronger than ordinary neutron stars. To put that in perspective, a typical refrigerator magnet has a field strength of about 0.01 Tesla. Earth's magnetic field is about 0.005 Tesla. A regular neutron star might reach 1 billion Tesla, but a magnetar, over a quadrillion Tesla. These are the most magnetic objects known in the universe. So where do magnetars come from? Not every neutron star becomes a magnetar. The conditions must be just right. The core collapse that leads to a neutron star must be asymmetric, perhaps with unusual rotation or intense turbulence. Some theories suggest that a rapidly spinning core during formation may wind up magnetic field lines to incredible strengths, creating the seeds of a magnetar. Others suggest that a high-energy birth event or merger can also produce one. However they form, only a small percentage of neutron stars, perhaps 1 in 10, become magnetars. Their powerful magnetic fields twist and stress the crust of the star, which is solid and brittle like the outer shell of Earth. Over time, this tension can snap the crust, unleashing violent outbursts called starquakes. These starquakes release intense bursts of X-rays and gamma rays, sometimes in milliseconds, and sometimes with dramatic tails that last for hours. The energy released in a single flare can equal the total output of the Sun over 100,000 years. On Earth, we are largely shielded from these distant events. But magnetar flares are powerful enough that if one occurred just a few light years away, it could damage our satellites or disrupt our atmosphere. In fact, one such flare was detected in 2004 from a magnetar called SGR 1806-20, about 50,000 light-years away. Even from that vast distance, the flare was so bright it briefly ionized the upper atmosphere of Earth and saturated gamma-ray detectors in space. This single event released more energy in 1/10 of a second than the Sun emits in 150,000 years. That's how powerful these objects are. But magnetars don't just emit flares. They can also affect their surroundings in more subtle ways. Their magnetic fields distort the space around them, bending light and warping particle trajectories. These effects allow us to study how matter behaves under extreme conditions that cannot be reproduced in any laboratory. And there's another mystery surrounding magnetars. They may be the source of one of the most perplexing astrophysical phenomena of the modern era: fast radio bursts, or FRBs. FRBs are intense, brief flashes of radio waves that last only milliseconds, yet release more energy than our sun does in days. First discovered in 2007, FRBs have puzzled astronomers ever since. Many come from distant galaxies, billions of light years away. Some occur once and never again. Others repeat sporadically. For years, their origin was unknown. Then in 2020, a breakthrough occurred. A fast radio burst was traced to a magnetar in our own galaxy, called SGR 1935-2154. This discovery linked FRBs to magnetars for the first time. The mechanism isn't fully understood, but it likely involves a sudden reconfiguration of the magnetar's magnetic field, a magnetic quake that sends shock waves through the surrounding plasma, creating a blast of radio energy. Still, the story is incomplete. Not all FRBs come from magnetars. Some may have different origins, such as black holes or neutron star mergers. But magnetars remain one of the most promising explanations. In this way, they serve as windows into physics at the extremes, where electromagnetism, gravity, and quantum mechanics collide. But the life of a neutron star doesn't end there. Over time, many neutron stars drift into obscurity. They cool, they slow down, and if isolated, they eventually fade from view. These dead neutron stars are nearly impossible to detect unless they interact with their environment. Some may become part of larger cosmic structures, absorbed into dense star clusters or pulled into galactic cores. Others may roam the galaxy alone for billions of years, dark and cold, barely distinguishable from the void around them. And yet, even in death, neutron stars have stories to tell. A collision may awaken them, a passing star may reignite their field, a gravitational wave detector may pick up their signature, or a telescope, aimed just right, may catch a pulse that travelled through space for thousands of years. Each one is a cosmic relic, a fossil of a supernova, an imprint of a massive star that once burned bright. And neutron stars are more than just astrophysical curiosities. They're test beds for the deepest laws of physics. Inside a neutron star, the known laws of matter are pushed to their limits. At the core, densities may approach those of quark matter, where the neutrons themselves dissolve into their constituent particles. Some theories suggest the center of a neutron star could contain a quark gluon plasma, a soup of subatomic particles once common in the early universe, just moments after the Big Bang. These are more than theoretical musings. Detecting the mass, radius, and vibration frequencies of neutron stars helps us test equations of state, formulas that describe how matter behaves under pressure. Telescopes like NASA's NICA, perched on the International Space Station, are designed to measure X-ray pulses from rotating neutron stars and infer their shapes and sizes. These observations give us clues about the structure of matter at nuclear densities. Meanwhile, gravitational wave detectors like LIGO, Virgo, and CAGRA continue to pick up signals from colliding neutron stars, providing complementary data on how matter behaves when crushed and spun at relativistic speeds. In every sense, neutron stars are natural laboratories, places where we can study physics in conditions that would destroy any human-made instrument. They help us answer questions that reach far beyond astronomy. What is the ultimate structure of matter? How do the fundamental forces interact? Where do the elements of life come from? The answers lie buried in a crust of neutron-rich nuclei, in a mantle of superfluid neutrons, in a core we can barely imagine. And through every pulse and flare, every ripple and wave, they whisper the answers. If we only know how to listen. These remnants of destruction become beacons of knowledge, teaching us not just how stars die, but how nature works at the very edge of what is possible. Neutron stars are remarkable not only because of what they are, but also because of how they behave. Some remain relatively quiet, spinning steadily through space. Others, however, interact violently with their environment, producing spectacular displays of energy and motion. One of the most astonishing manifestations of such activity is the formation of X-ray binaries. An X-ray binary occurs when a neutron star is part of a two-star system. In this cosmic pairing, the neutron star orbits another, more ordinary star, usually a main sequence star or a red giant. Because neutron stars are incredibly dense and compact, they exert powerful gravitational pulls. If the two stars are close enough, the neutron star can begin to siphon gas from its companion. This process is called accretion, and it's anything but gentle. The gas spirals inward, forming a swirling disk around the neutron star. As it balls, the gas is compressed and heated to millions of degrees. The friction and compression within this accretion disk generate immense energy, much of it released in the form of X-rays. That's why we call them X-ray binaries, because the intense radiation from these systems can be detected even from thousands of light years away. Some of the most famous neutron stars we've ever discovered were found by observing these X-ray emissions. One classic example is Scorpius X1, the brightest persistent X-ray source in the sky outside our solar system. Discovered in 1962, it was among the first cosmic X-ray sources ever detected and remains one of the most studied neutron star systems to this day. These X-ray binaries don't just glow, they flicker, flare, and pulse. As matter pours into the neutron star, sudden changes in flow or instability in the disk can cause bursts of energy. Some systems exhibit X-ray bursts, brief but intense flashes caused when accumulated material on the neutron star's surface suddenly undergoes thermonuclear fusion. These bursts can last seconds to minutes, releasing the energy of billions of atomic bombs. But there's even more drama in store when neutron stars form millisecond pulsars. A millisecond pulsar is a neutron star that spins incredibly fast, hundreds of times per second. Some rotate more than 700 times per second, faster than a kitchen blender. These dizzying speeds are achieved through a process known as spin-up. Imagine a neutron star in a binary system gradually pulling in matter from its companion. Along with the matter comes angular momentum, the property of rotation. Over time, the neutron star is spun faster and faster, like a skater pulling in their arms during a spin. Eventually, the star reaches astonishing rotation speeds, becoming a millisecond pulsar. These rapidly spinning neutron stars emit beams of radiation like lighthouses. When the beam sweeps past Earth, we detect a pulse. Because of their extreme stability, millisecond pulsars have been used for incredibly precise timing measurements, some rivaling the accuracy of atomic clocks. In fact, a global network of pulsar timing observations, called pulsar timing arrays, is now being used to detect low-frequency gravitational waves from supermassive black hole mergers. These pulsars are helping us probe the structure of space-time on galactic scales. Neutron stars, once born in violent explosions, evolve into cosmic clocks and high-energy engines. But some of the most dramatic events in their lifespans come not from what they emit, but what they collide with. One of the most spectacular events in modern astronomy was the collision of two neutron stars, observed on August 17, 2017. For the first time, gravitational wave observatories and traditional telescopes witnessed the same cosmic event from two different messengers: ripples in space-time and bursts of electromagnetic radiation. The event, known as GW 170817, was a neutron star merger that sent a gravitational shockwave across the universe. Just 1.7 seconds later, a gamma-ray burst was observed, followed by a glowing cloud of heavy elements, what we call a kilonova. This kilonova, visible for days across the spectrum, was direct evidence that such collisions forged some of the heaviest elements in the periodic table: gold, platinum, uranium. For decades, scientists wondered where these elements came from. Supernovae alone couldn't account for them. But now we know, the smashing together of neutron stars can create them. Every ring on a finger, every gold coin, every trace of platinum in your electronics may have come from a neutron star collision. From death came creation, and the science keeps evolving. The study of neutron stars continues to challenge our understanding of gravity, quantum mechanics, and nuclear physics. We now explore concepts like hybrid stars, objects that might contain both nuclear matter and exotic forms of quark matter. Some propose the existence of strange stars, made entirely of strange quarks, more stable than neutron stars, and perhaps even more compact. These ideas remain speculative, but they are motivated by a deeper question. What truly happens to matter under such pressure? Does it remain a soup of neutrons? Does it collapse into pure quarks? Does it open the door to new forces or particles not yet observed? To answer these questions, scientists build increasingly sophisticated models and detectors. Missions like the Square Kilometre Array, SKA, will allow us to find and time more pulsars with greater precision. Gravitational wave observatories will continue to expand, detecting more neutron star mergers, and perhaps spotting ones we can't even imagine yet.
And quantum physicists are collaborating with astrophysicists to refine the equation of state for neutron matter, charting how pressure, temperature, and density interact in these exotic environments.
Ultimately, neutron stars stand at the crossroads of many sciences. They are not only the remnants of stellar explosions, but the stepping stones to understanding matter, space, time, and everything in between. They remind us that even in death, the universe is active, that when stars fall, they do not vanish quietly. They leave behind pulsars that keep time, magnetars that tear space, and collisions that paint the cosmos with gold. They show us that the boundary between collapse and rebirth is often one and the same. And in this quiet, spinning, humming corpse of a star, we find the echoes of physics that governed the early universe and still governs the stars above us now.